So Sasha is making the videos, and I will tell you what, the place to log in and get them.
It's already on desk in the red corner.
He did. He's perfectly organized. And, very good. And I will also, I think I sent some notes around to everybody, but in general I will put the notes on the website also, so you can pick them up. And at first I will give you examples of what I mean by asking your own questions about this and your own answers, so you have in mind what I'm thinking about. But for now, let's just start again with a little bit of review. We are considering V to be an open set in the complex plane. So D might be somewhat mysterious, with some interesting holes in it, perhaps, having interesting topology, possibly. And the complex plane is just a one-dimensional complex vector space, so it's really a simple thing. Let's say V with a basis, say, I don't know, call it E over the complex numbers, so that every vector has a coordinate which I will call Z of V, and we will write Z of V just as Z to be I will call that the standard linear coordinate. I'm being a bit pedantic here, but I want to know what Z is, because we use Z all the time. So Z is the standard linear coordinate. Oh, hi. Standard linear coordinate. And for example, functions, so examples of functions, for example, f may be even convergent with a convergent power, with maybe a convergent series, maybe not. Smooth function on E. So infinitely often differentiable with the Taylor series, and I've developed, in this case, at a point Z0, which I call 0, because there's no Z0 here in D. I will quite often do that, just take Z0, the base point from the development, to be 0. So maybe here is 0. So smooth function means infinitely differentiable at every point, and so we write f is C infinity D. So infinitely often continuously differentiable. So infinitely often space of infinitely often. Continuous differential. continuously differentiable. Functions. Indeed. So of course, complex values. So everything here is, well, not everything, but I'm thinking in terms of complex value functions. Now, far less differentiable, just one-time differentiable. This means, as you all know very well, but let me just write it down. You can expand this function. By the way, every applied scientist thinks in terms of expanding functions somehow or another. Right? And well, Deepak is true, right? Every physicist expands functions and has a good expansion, a good first order expansion, which I write A. Now I'm being a little bit precise. And using the coordinate, we have the advantage of being able to write down the affine part of the function, so translation, and then this essential linear after the translation here. So this is the affine part. Yeah. And of course, this is not true in general, plus small error term. So just one-time differentiable, that's those functions. And you might wonder what this norm is. This norm is canonical. Once you have the coordinate, it is canonically defined. So norm of z squared is z times z bar. So when you have that conjugation, you automatically have the norm squared. And it gives the standard topology on the vector space. There's a unique vector space topology with obvious properties. So we have a distance function, we have the notion of linearity and differentiability and so on. And then the definition of holomorphic. So holomorphic is a priori far less regular than smooth. It means that for every z0 in D, so it's, yeah, it follows that a limit exists. Limit z goes to z0. Well, yeah, let me write it this way. It's z goes to z0, f of z minus f of z0 over z minus z0. The usual thing that you would expect from beginning analysis exists. That means it's well defined and exists as a complex number. And the notation is that we call this the first derivative of f at the point z0. The word here is holomorphic. And just, there's some jokes about, well, it's why it's called O. You maybe know the jokes because in French you cannot say H. So holomorphique. And so the French decided to call it O. So it's French compatible. Sasha. So that's that thing. And this implies that f equals f of z0 plus this derivative term at z0 and times z minus z0. This would be wonderful if f were just an affine function. But you see, this part cannot be there. This part is not there. So this is just plus this small error term. So in particular, f is differentiable. So it's differentiable, but it's differentiable in a special way. Let me write it, emphasize it in this language here. A equals what we're calling, and I'll even write it in another way, the partial with respect to z at z0, which we will call f prime. In this case, and b equals 0. So it's a special kind of differentiability. At least at the infinitesimal level, you see no variable z bar. So at the first order level, we have no z bar. Now, in general, just to get the notation straight, the standard notation in complex analysis, in general, we write, just as you would expect, we write f equals f of z0. You're getting tired of me doing this, I'm sorry. Partial derivative of z with respect to z at z0. Times z minus z0. That's the definition of this partial derivative, plus partial derivative of f with respect to z bar at z0 times z minus z0 bar plus a small term. So that's the way you write a general differentiable function, just as notation. Okay. And then if you want to compute, if you write f equals u plus iv, every place in complex analysis in the world, you use here u and v. So u is the real part and v is the imaginary part of this thing. U plus iv. And u is a function, we think, a function of x and y. And v is a function of x and y. So these are real functions on the domain as a domain in the real plane. V is a function of x and y. And z equals x plus iy defines these variables, these coordinates x and y. Then the partial of f with respect to z, I mean, I know I've done this all my life, so I know by heart, but you can check this. This is just a calculation you will check. Is the partial of f with respect to x minus the partial of f with respect to y. There's a minus sign here. And of course, what the partial of f with respect to x is, this is the partial of u with respect to x. I'm just writing all these things down to make you mad at me because it's boring, but and similarly, the partial of f with respect to y is a similar calculation, and you will check easily then what these things are. with respect to z bar, there's a half always, and here is plus. There's a reason here, it's interesting, here's a minus, and then you bar it. Well, you bar it, you get a plus. So another little, then the key remark here that you keep in the back of your mind, keep things straight, is that f is holomorphic means that f is differentiable and the derivative of f with respect to z bar is 0. Okay. Now, of course, that means that's 0, and in terms of u and v, let me emphasize that's a complex equation of complex numbers. And let me emphasize that the mathematicians early in the 19th century, people like Cauchy, really didn't believe that one complex equation is an equation. They always regarded this as two equations. Right? It is a big psychological jump to say, it's a complex equation. Come on, give me a break. Yeah, it's a complex equation. If you're the quaternions, it's one quaternion equation. It's not somehow some huge number of equations. Right? There's no reason. It's whatever the variable is, whatever's going on. So in terms of u and v, the way Cauchy would consider this, and maybe a little bit Riemann at first, you have what are called the Cauchy-Riemann equations. Which is partial of u with respect to x minus partial of v with respect to y equals 0, and partial of u with respect to y plus partial of v with respect to x equals 0. This is a system. You just check out what this one complex equation means. It means these two real equations. You just check it out. These are called the Cauchy-Riemann equations. And this is how Cauchy thought about things. Yeah. And the early physicists, that's how, for example, Green and such physicists thought about things this way. I advise you to think about things this way. Okay. So-called D-bar equation. As you notice, these are it's a very simple-minded system of partial differential equations. You might be amused. Yes, ma'am.
I have a question regarding the small.
You know, I have to come over and listen to you.
I have a question regarding the small o. Why is the small o of the absolute value of z minus z0 and not just z minus z0?
Because it is a term. It is a term that is smaller than the norm of z minus z0.
But it might.
What is little o? She's asking, what does little o mean?
Yes.
Okay, it's a function, right, which is smaller than z minus z0. This means that if you divide this function by the norm of z minus z0, it goes to 0.
But it might have z and z bar. And
It might have anything. It might be just, yeah, it's very good. It might be anything. But it's smaller than z minus z0. That's just the way to say it, right? Little o. Okay, it's smaller than z minus z0. You divide it by the norm. I don't want to divide it by z minus z0 because that's a very delicate thing if you're talking about something. Yeah, I divide it by the norm.
yes, but if o, small o might have z bars in it.
Yes, sure.
So why can you say that f is only a function of z?
I didn't say it. I said at least infinitesimally. Where did I write that? If I said it
At the first order letter, okay.
here infinitesimally, at first order development, is a function of z.
Okay.
It's very good that she makes me repeat this, because this is the key thing. This is a very weak condition. Infinitesimally, its first order development looks wonderful. It looks like an affine function of z. Right? So Otherwise, it's a terrible, the linear part is a terrible thing. You understand? The linear part would then be terrible. It would be a terrible linear function. Okay? So, the theorem that I will now prove is an example of the first regularity theorem that maybe the beginning students will have seen in mathematics. And regularity means usually you start with some function or something that looks pretty terrible, and then you prove that under certain conditions it in fact is not so terrible, it's regular. So the regularity theorem and I will use this proof of Gauss-Sab, but I think this is the first time that anything was proved carefully. Probably in the late 19th century, so after Riemann. Although Riemann, I think, did this too. Is if F is holomorphic on D, and Z is an element of D, and F equals, and this means convergent equals, a convergent power series in the neighborhood of Z0. So this is what Maria was talking about. I said infinitesimally, and that's the definition, but then there's the theorem that the thing is a power series in Z. So it not only doesn't depend on Z bar in any way, it's a power series in Z, which is convergent power series. We'll talk about convergence, of course, but I think you've talked about convergence before, you know what I mean. So it's a convergent power series to F in a neighborhood of D. So D is, if you like, perhaps mysterious, and you have some holes in D and so on, and you have a point Z0, and you have then a disk in here, and my notation, if the disk is radius R, so I put as big a disk as I can in here, and I call this disk of radius R about Z0. So it will be convergent on some disk, and in fact I'm going to show you on the biggest possible disk you can put in the domain where the thing is defined. That's fantastic, huh? So on a disk of radius R around Z0, and I say a C picture. Okay, so that's a wonderful regularity theorem. You only know that it has a first order development that's reasonable, and it is of fundamental importance, and this was the point that many people in the early part of the subject weren't careful about, maybe they didn't care about it. It is of fundamental importance. I do not say anything about the regularity of the derivative. It could be differentiable, but the derivative could be anything, a priori. This is the problem. So, this is the problem. So, as the first goal today, in the next 15 minutes or so, I would like to prove this theorem because it is a very elementary thing, this theorem. It's very surprising. Yeah. I see some faces from physics and so on. Let me make a remark. There is another weak definition of holomorphic. which is completely standard in the area of PDE. And quite often you will see this in the applied sciences. PDE means partial differential equations. Okay? And I recommend that you think about this a little bit. We say that F is weakly holomorphic. If and only if. Okay, here we go. I'm going to do something terrible that any applied scientist does and doesn't worry about it. If and only if the integral of d bar f against rho, no, rho is bad, phi, against d volume over d is 0 for all phi of compact support. Get used to it. This is analysis. My viewpoint is not necessarily analytic all the time. Sometimes it is. I can go many ways. I can go analytic, I can go geometric, I can go algebraic. I believe we should all do this in mathematics. This is a very analytic viewpoint. You have the usual volume form on D, integration over D. And if d bar f is 0, then obviously this integral is 0. Right? And this integral makes sense because this thing is of compact support, so that means it looks like a cutoff function, so it's not a dangerous integral, so this looks good. But the trouble is, you don't know what d bar f is because f might not even be continuous. It might not, you see, you don't worry if you're an applied scientist, you should write it down first of all. Then get used to it, it's good. It's really good, I've learned this. But it's really good to make the next step also. Yeah? And then the next step here is the next step is to do integration by parts. Now, you are just beginning students in mathematics. Of course, everybody in this audience knows what integration by parts is, and you know the standard notation everywhere in the world. We also use U and V also, and for some unknown reason, you write something like this all the time, and then then you want to integrate, and this thing you can integrate. Because it's derivative of something, that's the same as integrating that plus that, right? So you see, if one of these things is zero, well, what do you do when you integrate here? I'm warming up to this. Let's just say for fun, this is applied calculus minus 15. So this is integral from A to B. Yeah, somebody here is grading for applied calculus. You're grading, you see. This is applied calculus. No, this is really applied calculus. So, so you know how to do this, right? And this is U, V evaluated from A to B, right? That's what you do. Yeah. But there's if you're lucky, one of these functions is 0 at A and B, right? If you're lucky. That's the usual luck. Usual luck is both these functions here, but then you think of what the situation is. This is an interval AB, and AB looks like AB, and then you say, what the heck is AB? Is this B minus A business? So the boundary of this thing is simply B minus A. Isn't it true? The boundary of an interval is B minus A. Now that looks formal, but that is not formal. B minus, look, here's the bound, here's A, and here's B. This is for Jasper, right? For Jasper, because he's grading for applied calculus, minus 15. So this is that, and you know, as the students of mine in analysis 1, that an interval really has an orientation because you're decomposing this interval and you have xi plus 1 minus xi. So you really have a sign going here, so there's an orientation of the integral, right? So this thing is flowing out and this thing's flowing in. So the boundary of this thing is b minus a. Okay? So what this says is, by integration by parts, is you have this thing on the left-hand side, which is two things, right, is a boundary integral. And if one of these things is 0 on the boundary, you're in big-time business. And if one of these things has compact support, where the devil did it go? Oh, here it is. If one of these things has compact support, this guy has compact support, that means the boundary integral that you're going to get is 0. Because compact support means it's 0 on the boundary. The support is inside, right? So that means the boundary integral is nothing. That means that you did Kapitalismus. This is Kapitalismus im Sinne von Karl Marx aus Trier in Deutschland. So, yeah, this is Kapitalismus. You pay your money and you take your choice. You can either integrate this derivative times phi, or this thing times the derivative of phi. And usually you pay your money by having a boundary integral, right? But if the thing has compact support, Karl Marx would say, you see, capitalism fails. You have socialism. You don't have any cost whatsoever. So you see, if phi has compact support, then that means the integral of the derivative of f with z bar phi equals, you have to think of maybe a little bit here, maybe there's a sign difference, f, the integral of this thing times this. You push the derivative on the other thing. Now look at that equation. At nighttime, when you're very tired and have drunk a lot of wine, and maybe the wine is even bad, but you can be very happy about this equation. The left-hand side probably does not make sense, so we don't even know anything about f and its derivative. The right-hand side, at least if f is continuous, the right-hand side makes perfectly good sense because we have, what did I say phi was? What did I say about phi? Compact support, smooth. Smooth. Otherwise, I'm in big trouble. So I don't know what the devil about the derivative of f. I push it over onto phi. This is a standard trick, but it's called integration by parts. It's sometimes called Stokes' theorem. You push the derivative over to the other side, and you have this equation equals 0 here. You should think of this as a pairing, and you should think of this as a pairing, and this pairs this thing with that, and it says that this operator is more or less self-adjoint. It means that you push over discussion about the operator with the adjoint operator. If you haven't had much linear algebra, you haven't had this experience yet. It's like you haven't had your first date yet. But it's very important to understand that you can, this silly thing about integration by parts, you can push over a differential operator over to something smooth, and then this thing isn't even defined, and so you define holomorphic this way. Okay? You define holomorphic that way. Okay, that's called weakly holomorphic in the sense of distributions and so on. Okay? This works beautifully for the D-bar operator. And it's a nice theorem that you can check a function is weakly holomorphic in this sense if and only if it is a power series. And that's an example of standard regularity theory in the first theory of partial differential equations. In this case, the background operator is an elliptic operator. Let me just comment on what is going on in the background. What is going on in the background, if you're a little bit correct, yes, up here.
Quick question, you said it's self-adjoint. What is the operator exactly?
No, it's not, but
Okay. Almost.
essentially, and yeah, that's right. What is really your favorite self-adjoint operator? So he's studied a bit the partial differential equations. I think you talked about maybe. I don't. And what is really good here, and is really at the heart of the matter, and you'll believe, any physicist here will believe that we're really in business here when I do the following calculation. Let's just see the second partial of u with respect to x plus the second partial of u with respect to y. Any physicist here would be very happy to understand the role of the Laplace operator here in this thing, and that's really what is going on in the background, is the Laplacian is playing a role here in complex analysis. As soon as you have the regularity theorem, of course, I'm not allowed to do this. U and V are just terrible functions. How can I take a second derivative? But the end result is that there's everything smooth, so let's not worry about it. If you look, this thing is zero. So u and v are what are called harmonic functions. Now, I'm not allowed to do that yet because I'm not allowed to take second derivatives, but I will prove this regularity theorem as soon as I have any kind of regularity theorem. And what Appik was really asking about, that is the elliptic regularity in the background here is for the Laplacian. Okay. So the Laplacian is in the background of complex analysis, and the reason is. Okay, let me prove the regularity theorem so that all of this stuff makes sense. Okay, so the regularity theorem proof. And so, proof of regularity. Now somebody asked, I think you asked, literature here that I know about is Alfors. So there's precisely one book there's several books by Alfors. I know two at least, both beautiful. Alfors writes beautifully. This is just complex analysis. And I think I mentioned a very nice book last time we were here of Eli Stein. And I don't know what it's called, but it is a very nice book. Complex analysis, something like that. And Stein, one of Stein's students, who I know quite well, Steve Krantz, I think he writes beautifully also, so if you want to look at Steve Krantz's books on the subject, it's fine. And as I said, I provide notes and videos, so you can't go wrong. Okay. Now, I was a friend of all these guys. Okay. De Gourzat-idee. Gourzat-idee. The idea of Gourzat is to show that if you have a rectangle, then the integral around the boundary of the, and f is holomorphic on the rectangle. And when I write a situation like this, I'm getting very tired already of this, and so are you. You see, a rectangle is a closed thing like that. For me, it's closed, with boundary. And when you have a closed thing like that, I mean holomorphic in a neighborhood of it. See, I defined holomorphic on open sets. So holomorphic in a neighborhood of an open set means holomorphic on an open set means holomorphic in a neighborhood of that set. That's the definition. So that means there's some neighborhood that maybe I call this df, which is a domain depending on f, could be smaller and smaller for different f's, which contains the closed rectangle. And I won't say that anymore. And it's very important because I'm going to consider boundary integrals. So his statement is that this thing is 0. Okay. Why on earth does that have to do with regularity? First of all, what does this mean? This is very mysterious. But if you know the history of this subject, you know that this is not mysterious at all. So the history of this subject goes back to physics, to Green, and then, of course, to Cauchy, and so on. So very old history of this subject. And people knew about the importance of this integral, and he had the idea of just checking it for something stupid, for a rectangle. This was the idea of Gourzat. Now I'm going to explain to you why that would be interesting to check that. Okay, I mean otherwise this just comes. God says check it on a rectangle. Check it on a rectangle. Yeah, well, okay, it's the simplest thing you could think of, actually, right? Circle it, you could probably also, because you have polar coordinates for a circle, but rectangle is it's linear. Yeah. Okay. Okay, so let's go into this. So first of all, step 1, integration. I'm going to talk about integrating. Okay. By the way, I was in the mountains this summer looking up at the mountains, trying to get motivation for this lecture. This very lecture, lecture 2 of complex analysis. Yeah. And I don't talk to God, but I enjoyed the mountains. It's so beautiful. And looking at the mountains, I thought maybe I would have something would come into my brain, because integration is a global thing, right? I mean, you integrate something. It's a global thing. So let me just. It's a global thing. Yeah? And here's an example, I think, of possibly even a deep question that you could ask yourself, and I ask myself in the mountains, looking at these beautiful mountains, the Dolomites, by the way. If you ever go to the Dolomites, I recommend. So, integration, but the regularity is basically local. It says it's right at each point is regular. So regularity looks local. It looks local. And I find it very disturbing. Not getting mad, but I find it disturbing for my own intuition why we need a global technology to work on local problems. It's something very deep going on, right? It must be very deep. That if we need something global to understand something local. Almost infinitesimal local, right? Regularity, you only care about what happens, right? Derivatives or power series expansion near a point or something like this. So, I am asking this question, why? That's one of my questions. If you could explain this to me, I would be very happy. Okay. Well, what is integration? I'll explain how I see integration. And in case you've had some experience, but I explained everything. Why is global technology necessary? Why is it necessary? So let's briefly discuss integration in over a curve in the plane. So everybody here knows about integration over an interval. It's more or less the same thing. So what is a curve in the plane? First of all, later on the complex plane, of course it doesn't matter. So what is a curve? A curve is a picture. Here's the plane. Now here's an interval. The interval has orientation, and a curve is a smooth, sufficiently smooth, at least one time continuously differentiable. Maybe we need more. So a smooth mapping into the plane. At first I draw it in a simple-minded way. Maybe it has self-intersections. Maybe it's terrible, but at least right now, for my picture, I'll just draw it like this. And it has an orientation, and you go from one endpoint to the other. Okay? It's a curve. And now, mathematics people maybe don't like to think physically, but I like to think physically a little bit. If we have a point here, it's a gamma. A point here is gamma of time t. So this is I think this is the t axis. And I think of a particle moving along this curve in time. But you don't need to, you can think any way you want. And of course, this thing has a velocity. And the velocity is a vector. And I drew a really fast velocity here, which we write as gamma point at t. Whenever you, in mathematics, see a point, you probably should believe that we're thinking about time and velocity and so on, as opposed to just a derivative. Okay, so you think of that guy running along that curve, and let's assume that gamma has two coordinates, x of t, gamma of t at time t is equal to x of t, y. And of course, gamma point of the derivative is what you think it is, of course. So this is just the derivative of these two things. Okay, that's the derivative. So at each point, x of y is the x and y coordinates. We're using them right now. Later on, I will use z and z bar, and the velocity of x point. Okay. Now, this curve is moving along in, if you like, some sort of field. Maybe you can think of force. Maybe there's some force pulling on this curve. I don't know. This field, whatever it is not tangential to the curve. It's anywhere. So let me draw it again. Here is gamma point, and here is this field. I'll call it F at the point gamma of t. This field is everywhere, but what's a field? A field's a vector. So we want to know how this field is acting on this curve. So how this field is acting on this curve, what we want to know is what is the projection of this field to the curve. Isn't that true? I mean, you want to know if it's orthogonal to this tangent vector, it's not, you can't do anything to the curve, I mean, right? But if it's tangential, it's really pushing on that curve, right? So we want to know its thing, its projection. Now, what is a projection? This field is it's going to be a function. It's going to depend on a function. This is a function. Let me just, what is this field going to be in general? It's going to be a function. Now I'm going to write something terrible that you're going to understand much better after a little bit of mathematical training. I'm going to write something terrible. I'm going to write a differential form. Okay? I'm going to write a differential form. What this differential form is, it tells you that at the time gamma, at the point gamma of t, you get this thing. Which you easily understand as the inner product of f with the velocity vector, with the, we'll write t here, which is the projection of f on gamma. Isn't it true the inner product is a projection? That's true, isn't it? This is true. Linear algebra. The first steps in linear algebra. Right? The inner product is the projection. Right? So if you take a thing that I'm calling, this is called a one form, but it doesn't matter because it's one form. How do you evaluate it? Well, you evaluate it on this velocity vector by projecting it into it. So it is, you just project the x part of it times the x derivative, and the y part of it times the y derivative. I mean, this is nothing. Right? It's projection of something. Can I call this force? Is it okay, maybe? And you talk about things in engineering science and physics and so on, about work to go from one place. You know, all these things that you learn about in applied sciences, you could read. All I'm saying is that if you have this force, this field which you can think of as force, but I'm calling it a one form. And this notation simply means I'm telling you how to evaluate it on a vector. I'm telling you how to project it. This says this thing dx. This is project f of dx, g dy. It's f derivative x, g derivative y. That's the inner product of this thing with that. That's the projection on that thing. Okay. Yes.
Why do you evaluate f and g as gamma prime and not gamma?
Oh, well, then I made some mistake. Thank you very much. No wonder, everybody. Yeah, it's at the point gamma of t. Thank you. Okay, that's how you evaluate a one form. Think of it that way. And now everybody in this room understands then the integral of. So I've written this as f, but quite often I will call it omega, of a one form omega. I wrote it as f, trying to think of it as a force field. The integral of gamma over omega is just simply integral a to b of this inner product. So f, I'll write it all out. The f part gets hit with the x part because we're taking the inner product, and the g gets hit with the y part. So that's the integral over a curve. Okay? Okay? Well, that's just the usual integral of analysis 1. Yeah? And if you look at it for a minute, you see that it really doesn't depend on the parameterization. Because if you change the parameter, you have the substitution rule, and that will, you will just get an integral. So it's really a perfect thing. Okay. So since that is the case, we now have an integral over curves. And now, the integral over a curve of a complex value function, f dz, okay, is the obvious thing. You just extend by linearity. So I'm going to write it down one time, and it'll get on your nerves, but let's see here. Integral of u plus iv dx plus I dy, and that's equal to all sorts of stuff here, terrible gamma, u, let me try to get it in real and imaginary parts, u dx minus v dy plus I times v dx takes the udy. Okay? So this is how this complex guy is defined. Okay? That's the first thing, curve variables. Then we make a remark. Let's just take omega a special form. Let's take omega equal to this form. Partial of h x dx, partial h y dy. Okay? Okay. Let's take this special form. This is called d of h. You all are familiar with gradient, I hope. Yeah? Gradient is a well-known notion. This is essentially the gradient. When you see the letter gradient, you think that is the direction where h is growing. If you take something tangent to the level surface of h, it's not growing there because it's just tangent to it. If you take something orthogonal to it, that's the best direction where it's going. This is orthogonal to the level surface of h. H equals the constant. And here's the tangent space of h equals the constant. And here is the gradient of h. Okay. Now this fantastic physicist, mathematician named Green, understood all of this stuff. It's a very wonderful story. You can read about it. I love the story. He was a self-taught scientist who had to work for his father, who was a baker, and Green had to make sure that the windmill, you know, when you have grain what do you do to the grain? You need the windmill to make the grain. He was responsible for working with his father, in particular this windmill, and he used to love to go up in the windmill and think. And he proved with physics methods. When I talk, I see some physicists here. When I say physics methods, I'm not insulting physicists. It's very early in science, long before Riemann and so on. So he proved with physics methods Green's theorem. And I am sure, I'm not a good historian of science, but I am sure he was thinking about flux or flow through some kind of surface. Probably some kind of medium. Yes? And it's one of these things you can compute what's going on inside by what happens at the boundary. You believe it. What flows in and out at the boundary determines what's going on inside. That's physics. And Green made that precise in Green's theory. And what Green certainly had in mind was this. Green said, if this guy is a gradient, let me then write this as f dx plus g dy. And here's the curve, and here is the velocity. This curve is maybe bounding something for Green. So this curve is the boundary, oriented boundary of some domain. All right, we're got a domain in the plane, and the curve now is maybe only piecewise smooth, but that means transversal to the boundaries. Piecewise smooth, but that doesn't matter. Just the integral are just some of the integrals, right? And he's thinking about what's going on, and he's thinking about gradient of A. He's thinking about gradient fields. This is a gradient field if it's like this. And then if you look at this field, look what happens to it. Well, what is D? He defined, I don't know whether it was Green, but very close to Green, D of this thing, the boundary of this thing, to be, well, df, dy, well, let's do it out. It's the boundary of f, so the gradient of f, dx, plus the gradient of g, dy, and then you do a calculation here. This is the partial of, I did it up there, of x dx plus the partial of f dy dx plus, then you do this thing here, partial g dx plus partial g dy d1. Okay. Now, if you stare at that long enough, you see that this thing, when you consider it in the x direction, does not contribute. This thing has the false orientation. So actually this contributes minus this. So this thing is equal to, this is minus, well that's minus that, so I'll put plus of this one, that's dx dy, so that's g dx minus df dy dx dy. He understood that this is really the key thing to understand when you have a force field acting on a domain. Okay? And Green proved, what did I tell you in the blackboard here? Oh, it's gone. Green proved that the integral over the boundary of the domain of d of something, no, over the domain of d of something, so let's do this part first. d dy is the integral over the boundary of the thing of the guy. So there. That's integration by parts. And this guy, I just did the calculation, this is Green's calculation, is gx minus That's a quick introduction to integrals. Let me repeat what I've said. First of all, second year students here will now be taking what is called calculus on manifolds. This theorem, in the higher dimensional version of this, is called Stokes' theorem. You've heard of Stokes' theorem in calculus, probably. Calculus says Stokes' theorem, the elementary version of Stokes' theorem is for rectangles. The integral in the plane. The integral of something like, here, this is Stokes' theorem. Oh, I wrote dr here. Nadia, you should have caught me here. Anything. Okay. The statement is, a boundary integral is equal to an area integral, which is an incredible thing. Yes, a boundary integral is equal to an area integral. You've seen it. A boundary integration by parts. The boundary integral is equal to an area integral. It's integration by parts. And this has to do with the way something flows in here. And now let's look. Suppose, this is how Green understood this thing. Let's suppose that the omega, let's call this thing omega. Yeah. And suppose omega is equal to a gradient in the above sense. That means omega is equal to the derivative of x dx plus the derivative of y dy. And now, what is d of that thing? D of omega, what does our law show us someplace? I've gone very quickly here. Here. It's partial x, partial gx minus partial fy. Okay? So that is partial gx minus partial, partial gx, that's g here, right? Minus partial fy. What is that? Wait a minute. Let's be careful. Partial gx minus partial, let's be careful. Yeah? Yeah? You know why I'm being careful. It is a theorem that the mixed partials are equal if you change the order.
Even though I think you wrote it the other way around on the side. You wrote, you knew about dg dx?
This?
Yeah. So it should be divide dx and then dx dy on the other side.
So, dg dx, where are you objecting?
Oh, because it says dg over dx. So the already regarded as df dx plus dg dy in the first line.
This line here.
One above.
Yeah.
So
you differentiate f and then wedge it with and hit it with
you
dx.
say so if f is dh dx,
Yes.
and f comes in the second place in the third row.
That's right. So
So it should
So what you get here, what I made a small discussion here, and you have to think even physically, is that this part dx is going to be 0. Okay, so only what's left is dy dx, and that orientation is wrong. So that's minus dx dy. So what's left over is minus df dy.
Yeah. And since f is
And what I wrote.
dx,
Okay, so this probably I did it wrong. Let's see, this is in the notation, I did it exactly no, I did it right. This is F and this is G.
yeah.
Okay, so it's dx dy, dg dy, so dg dx, which is that, minus df dy.
sure if agree matters then here, but I mean, if we, that means the notation in the line means that we differentiate first with respect to x and then with respect to.
Oh, it's a question of which, what means.
Yeah.
For me, the notation means first y and then x.
Ah, okay, yeah, okay, yeah. That's-
I don't know. That's my notation. I don't know. Okay. Anyway, with very small regularity, this is zero. But you see, regularity plays a role here. Okay. 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 Now. What was known, if you believe Cauchy, is that f is holomorphic if and only if d of f dz equals 0. And so if you believe Green, and none of these things were proved until Goussat, if you believe Green, then implies that the integral of around the boundary of d of f dz, if f is holomorphic, equals the integral of d of f of dz around d, yeah, which is 0 because this guy is 0. Okay. That's very sketchy for one thing because there's no sense in my going into integration theory because either you've studied integration theory before, calculus on manifolds, or will study it now in calculus on manifolds. But this first step in integration theory tells you that the integral of a form omega around the boundary is equal to the integral of its differential along the inside, and the differential, the way Green calculated, is this. And if the original thing is f dz, where f is holomorphic, then you compute out that d of f dz is 0. That d of f dz is the Cauchy-Riemann equation. This thing is 0. By the Cauchy-Riemann equation. So this was completely known to Green, was completely known to Cauchy, was completely known to Riemann, historically. And nobody worried about smoothness. Everybody believes the theorem of Green because you don't need anything. Green needs smoothness. In order to prove Green's theorem, I don't know who proved it the first time, Stokes' theorem. Stokes didn't prove it the first time either. I think the first decent proof of this theorem was probably due to Bourbaki in the 1940s, correctly, where smoothness was correctly used, where differential forms were correctly used, where calculus on manifolds, which you will learn, was correctly done, and it's now finished. Right? You need smoothness. So for Stokes' theorem is this theorem, the integral around the boundary of d of omega is d omega over that. You need smoothness here. You can't just take the differential and go home and drink a cognac. Yeah? You need smoothness, right? And you don't have it. You only have that the function is differentiable, and you need this derivative is integrable. So you need that this thing, some sort of regularity on the derivative. Okay? Regularity you need is that the derivative is continuous, so this integral will make sense. Okay? And Goussat, which I'll prove next time, Goussat, with a very clever argument, using an integration argument, proved it. Okay, that's where I'm going. Just to prove this for fun, you can see it. Now you can close your eyes, you have smoothness, power series development, everything's great. Okay, see you next time.